Okay, so yesterday we were doing at the end the massless spin 1/2 particle that describes objects like the neutrino, so they're quite important. And well, the equation was the following. Well, these are the alpha matrices of Dirac. This is the P operator of derivative. Okay, and we don't have the beta matrix because that is multiplied by m, and we take m 0. The alpha I have the usual anti-commutation relation. When I put curly brackets, it means anti-commutation, delta ij. And I said, well, we don't have to go to 4-dimensional because this is the only things that matter, this algebra. And this algebra is realized by the sigma matrices. Another manner, and so basically we bring down that to a two-dimensional equation, okay, because now this is two-dimensional, so we need just spinors that are two-dimensional. But there was another manner to realize that the massless particles are described by two-dimensional, is to change representation of the alpha matrix. If you remember, the alpha matrix have to satisfy this relation, where this is the 4x4 things, that alpha beta plus beta alpha I is equal 0, that alpha E square equal beta square equal the identity. Now, well, and we had used what we call the Dirac realization of this matrix that is done in this manner, 0, sigma I, 0, where these are the Pauli sigma matrix, m beta equal I, 0, 0, I. But there is another realization that we called yesterday the Weil realization, and is the following: sigma I, 0, 0 minus sigma I. The sigma are on the diagonal things, and the beta of the Weil, W stays for Weil, D stays for Dirac, is the following one: 0 minus the identity 0, where all these, also the identity, are 2x2 matrix. Then if we use the Weil representation, first of all, it is easy to see that they satisfy these, and these were the only things. You see, what the Dirac equation embeds is only an algebraic property, because this algebraic property was needed in order for the momentum and energy satisfy the mass-shell relation. Okay, so it can be realized by this, or it can be realized by this. Up to now we have used this. Let's now use, in this case, for the massless particle, this one. Let's write psi in this manner, phi plus, phi minus, where these are two-dimensional vectors. Okay, and then let's write again the Dirac equation, IH d psi dt equal minus IHC alpha I slash psi plus m0 c square beta. Psi, if we put the mass. If we don't put the mass, this term is not there. And now let's use, so this is not there, let's use the representation of the Weil representation for the matrix. If you use the Weil representation for the matrix, because it is diagonal in this, you get that this one goes into two decoupled equation, d phi plus dt equal minus IHC sigma dot A phi plus IH d phi minus dt equal plus IC H bar C sigma dot phi minus. Okay, so if there is no mass, these are two, yesterday we got to this point, there are two decoupled equations for the upper two component, the lower two component. If you add the mass, then things change, because if you add the mass, then you get m0 c square phi minus, and minus m0 c square phi plus, and then they are not anymore decoupled equation because the phi plus pulls in the phi minus. But this term is not there. So you see, these two equations are very similar. The only difference is in this sign. And we can go from one to the other just changing t minus t. Okay? So basically these two equations are equivalent. One goes into the other by t into minus t. That means it's enough for us to solve this one, because the solution we will get will be the same solution but with t into minus t. So it's enough to get the solution of this. And this is a two-dimensional equation like we had got here. So for the massless particle is enough to solve the two-dimensional equation. So let's solve yesterday. I am going quickly because this is the last part I did yesterday and we already went through it. Okay, so let me keep these two equations anyhow. Okay. Now, so let's solve this equation and let's choose a solution at fixed p. So let's choose solution that are a normalizing constant a px. This is the four-dimensional scalar product over h bar u plus p, where u is a function to be determined of p, and p times x is p0 x0 minus p times x. Well, if you plug these things into here, into this equation, you get this very simple equation, pi0 p0 u plus equals sigma dot p u plus. Okay? So do the derivative with respect to t, and what you get? You get pi0. And so on. Then there is an h bar here, an h bar there that cancel, and so on. And you are get down to this relation. Then I said yesterday, if you use the well-known relation this one that has this sigma matrix and multiply by sigma dot p. Here, let's multiply by sigma dot p. If you do that, on the right-hand side, you use this identity and you get p squared. On the left-hand side, you use this, you get this. But then you replace pi0 with this and you get the same thing again 2 times. Okay, so that means I take, sorry, vice versa. I apply this on this, I have to use this relation and I get a pi square, a vector pi square. This is 0. Then I apply to this, I pull out the p0, I have sigma dot p, but sigma dot p is equal to pi0, so I get 2 times pi0. So the net result, if you apply this, is the following: pi square minus p square equals 0. So pi, the energy p0, is equal to the modulus of p. And that is what we know for a massless particle. But now let's go and solve. I think we got roughly to this point. Let's solve. Let's make a choice that p is parallel to the z-axis. Okay. Then this equation becomes the following one. P0 I replace with plus minus p u plus. Then I have, this is along z, so I have only sigma 3 p u plus. So basically I get sigma 3 u plus equal plus minus u plus. Now let's suppose we choose the positive energy solution. So let's choose positive energy. Then if I choose positive energy, the solution of this is nothing else than 1, 0. So positive energy is this, and let's calculate this helicity of this U plus. Well, you get immediately 1 U plus. So positive energy and helicity plus 1. If we choose negative energy, sigma 3 U plus equal minus, you understand, positive and negative energy is this object here. So I get minus, then the solution of this is 0, 1. So this is negative energy. And negative helicity. Now, we don't have in nature any particle that satisfies this because we have the neutrino, and the neutrino has negative helicity. That means the neutrino, if this is its momentum, its spin is always pointing in this direction. So the neutrino has negative helicity, but it has positive energy because it's a particle. So this psi plus cannot be a solution. The solution is the psi minus. And you know why things get reversed. It's very easy. You see this difference in sign here? Because of this difference in sign here, everything gets reversed. So instead of solving this, let's do the same step, but solving this equation. So here we have minus, U minus, minus, minus. But now, because of that minus sign there, here I have a minus sign. Okay? So I use the same things. This one I get, nevertheless I get. Here I have U minus, and I have minus. Then the solution, for example, of this with positive energy is this one because of this minus sign. Okay? So minus 1. So positive energy, helicity minus 1 for this case. Okay? In the other case, okay, let's choose the other case, minus, minus, with here a plus, and then the solution is this. And then I have negative energy, but positive helicity. So when I said the two are the same, well, modulo this minus sign, and this minus sign might identify one or the other with the physical thing. So the physical state is described by phi minus. The physical state, like the neutrino, is described by this object. Okay, so this is the neutrino. If it were massless, a positive energy solution, positive energy, but with negative helicity. Okay, now these things on the book is not, there is a lot of other things on the book, but just take these few things that I have done. Okay, this is page 333 and a few other pages, but don't go beyond the point in which he says the neutrino. There is a lot of blah, blah, blah on the neutrino and so on. Don't go beyond where he proves, like I did, that the phi minus is the solution. Okay. Now, there is a manner to project out the physical state. So anyhow, the result is, to describe a massless particle, you just need a two-component formalism. and you have just to see that, use the Weyl representation for the omega. In the case of the neutrino, it is a physical particle that has positive energy and negative helicity. We saw that of this two-dimensional equation, this one is the correct one, but this one might describe some other particle that we have not yet seen. Now, the last question I ask is, how do I get this solution from the general phi? There is a projector that might give me the general solution out of that. Yes, the answer is yes. There is a very well-known projector that you will find in particle physics many, many times. And this is the following, is the so-called chiral projector. Take the following operator, defined in this manner: 1/2 the identity minus gamma 5, where gamma 5, if you remember, it was defined as I, gamma 0, gamma 1, gamma 2, gamma 3. And if you use the Weyl representation of gamma 5, so the Weyl representation of gamma 5, that means you use for the gamma 0, so for the alpha, the Weyl representation, okay? So everybody is in the Weyl representation. Because remember, the gamma 0 you derive, and the gamma 1, gamma 2, gamma 3, you derive from the alpha. They are defined, if you remember, gamma 1 is alpha 1, beta, and so on and so forth. So if you use now the alpha in the Weyl representation, you get the gamma also in the Weyl representation. The gamma 5 in the Weyl representation has this nice form. So you see that this object in this nice form, this is the 4×4 identity minus this. Okay, so it's 2, and here I have a +1. Then I subtract that, and so what I get is 1/2, 0, 0, 0. No, that 1/2 is not there anymore. And then you see that with this operator, if this is the chiral plus, when you do on pi plus phi minus, you get exactly phi minus. That is the physical solution we wanted. So this is called chiral projector or chiral operator. And this object is also called left-handed. So the neutrino are left-handed. It means when you hear they are left-handed that their helicity is negative. Okay? Okay, so this is all we do on massless particle. There are many more things to do, but we will. So from page 333, just go on and. Okay. Now we start other two discrete symmetry. Up to now we have studied just space reflection. Today the last two discrete symmetry we study is charge conjugation for the Dirac particle. We already saw charge conjugation for the Klein-Gordon. Okay, and we will do today the charge conjugation. But before doing that, we have to explain the whole theory of Dirac. Well, Dirac, you know, had realized that in his theory, even if it was one-dimensional, if it was linear in T, and there was a probability interpretation, still there were negative energy. So he invented the concept of Dirac C. What is the concept of Dirac C? Well, he said, let's suppose that all these levels are populated by electron, one with spin up and one with spin down, one with spin up, one with spin down, one with spin up, one with spin down, and so on, okay? That all this is populated. In that manner, an electron from here, because the problem is having infinite negative energy, the system is not stable because a particle here could go down there, down there, down there, end up at minus infinity energy. So an electron, we know that the electron in the atoms instead, once they get to their ground state, they stay there. And they feel the relativistic effect because they go very fast and so on and so forth. They don't go to minus infinity. So why they don't feel this bottomless potential? Dirac had this idea, maybe there is a Dirac sea, there is a sea of populated by electrons, and then these cannot come here because there are already 2 electrons, one spin up, one spin down, and for the Pauli principle you cannot fit there a 3rd electron. So these electrons stay here, okay? Fine, this is the Dirac sea, but then somebody, I don't know who, asked him a question. Well, if there are infinite number of electrons, you have infinite charge and infinite energy. But, you know, what you measure actually is always difference in charges and difference in energy. So this minus infinity of energy and minus infinity of charge, you could put to 0. That means renormalize things, renormalize in the sense that as you measure only difference in energy, this one, even if it is minus infinity as energy and minus infinity as charge, because there are infinite particles, all they have to be populated, I could put this equals 0 and this equals 0 by convention. Why? Because the only things I measure are difference in energy. So this first problem, Dirac somehow with this convention is solved. But then, the other question is, okay, even if you have normalized and said, let's call that energy 0, because I measure only difference energy. If here there is an electron, I could excite him, I could give enough energy for him to jump here. How much energy do I need to give? Oh, I need to hit him with an energy equal to the gap, 2 m0 gamma 0. It would end up there. So, do you see this effect that you give some a huge amount of energy, 2 times the mass of the things, and an electron pop up? Well, if an electron pops up there, then here there is a hole, right? Because the electron has gone away. And the point is that these, first of all, there would not be charge conservation. If I give a lot of energy and all of a sudden an electron appears, these remember a charge 0. And an electron appears, it means there is no charge conservation. So that cannot happen. It means that the hole, that is why, the hole left here must behave as a positive particle. So that effectively when you create, when you give this amount of energy, you got an electron there, but it's not alone. It has also another object that he calls hole, because it's a hole in these kind of things, that must behave as a positive energy, a positive charge, because in that manner charge is conserved. We had created an electron, but behind we left a hole that behaves as if it were with a positive charge. Then charge is conserved. Good, okay? But the other thing is this hole not only must behave as positive energy, so that the positive charge, so that charge is conserved, but it must behave with an object that carry a mass and the total energy related to the mass equal to m0 gamma 0, because this is the amount of things we gave. So we have created an electron, we have left behind something that must behave as positive charge, otherwise charge is not conserved. But we also now have 2 objects whose total energy must be equal to the energy that is being absorbed. The energy that is being absorbed was this. It means this object effectively has a mass like that one, okay? So that this hole that is left there is actually a particle with positive charge. And this is what is called the antiparticle. So Dirac, in this manner, with the hole theory, managed to solve the problem of charge conservation, and also to find out that these objects behave like a positive particle. So this object, this hole that behaves as positive particle, equals, so the hole behaves as a positive charge particle of mass m0. Okay. And of course, you know, as the total energy that we had given is this, his energy is positive. So now even if it is down here, his energy is positive because we have given this amount of energy. And we have given this amount of energy and the net result is only one particle. It's impossible. One particle with negative charge, this electron, no. Because we look and this electron has only this energy and is at rest. So it means what is left behind, that is the hole, for conservation of charge must behave as a positive charge object and it must have positive energy, okay? So this hole, this solution, let's call psi c. So we have this that is described by our usual wave function of Dirac and this one that is described by the usual, that is a particle with positive energy. Why positive energy? Because the total energy we have given is this. So this particle must have taken half of this because the first one took this, the second particle must have taken this. Okay, so the hole that is left behaves as a positive charge particle with a charge equal and opposite to the one of the electron and at the same time with positive energy. Okay, so this quantity is called antiparticle of the electron. So the antiparticle of the electron is what Dirac called Hall theory. But you saw here, this is a many-body formalism. Because you need an infinite thing, then you can pull out one at a time, but you are left with infinite thing. So anyhow, the whole theory of Dirac is a many-particle formalism, and you will treat it better in second quantization. Second quantization that you will do next year in field theory, treat, and the second quantization of the Dirac field is equivalent to the whole theory, but is much more powerful and much more. Now, yes, please. Yeah, okay. So here I had an electron before. Now I give this amount of energy, and then this electron that was at these things will go up and will become a real electron. And behind there will be a hole. There is no electron anymore there. The electron has jumped there, right? And this is an electron with charge minus. So you have given a lot of energy to the vacuum. This is the vacuum. And jump out one electron. Oh, come on, it's impossible. There is no charge conservation because this is the vacuum. Remember, and the vacuum, we put all the charge and the energy was minus infinity, but we have normalized it to 0. And we have normalized to 0 because it's only the difference that we see. So the charge of this Dirac C is 0, and the energy of this Dirac C is 0. Okay? Now, if one electron come out, it means from 0 charge, it appears one electron. That cannot be because from 0 charge to one electron, there is no charge conservation. So it means that what is left behind, that was this hole, must behave as a positive charge particle. Otherwise, there would not be charge conservation. You understand? We have irradiated the vacuum with this amount of energy, and one particle come out, no, and charge is impossible, because then charge would not be conserved, okay? And then it means this one effectively behave as a positive charge. So altogether, the sum of the two is 0, like it was before.
Okay. How did you explain the charge conservation before the equation?
Oh yeah, before there was all this, and we had normalized to 0. So the charge before was 0, right? The charge before, with our convention, was 0. Before, there was no electron there, before we hit with the thing. And we had normalized this to 0. So at time minus 3 seconds, the total charge was 0. The electron was there. Why it was 0? Because we had normalized to 0 everything. There was no free electron. This was the vacuum. And we had normalized to 0. Then we give this amount of energy, and an electron jumps and goes there. Okay? So out of the vacuum now, at positive energy, we see an electron. So at t equal 5 seconds, Q is equal minus E. But then there is no energy conservation. Then it means that what is left behind, that is a hole, because the electron came out from there, must behave as a positive charge object, okay? So the hole we describe with the psi c, and it must behave as a positive particle, and the point is that it must behave with a positive energy, but with a positive charge, because in that manner, if the hole, the Q of the hole, so this is the Q of the electron, the Q of the hole was plus E, the sum would still be 0 like before, so we had energy. We would have charge conservation. What about energy? Because we gave this amount for him to jump this gap, but then we find out that this has only this energy. So where is the rest of the energy gone? It must be the energy of this particle, of the hole, because you know it's 2. There is a 2 here, and when I get up there, I only have this. It means that half of the energy is contained in the hole, and this is a positive energy. Okay, so the hole must behave as a positive particle with a positive charged particle with positive energy, and the mass the same, because this is the amount of energy we give, and we know that the electron got this amount of energy. If he is at rest, then it means the rest belongs to this hole. Okay?
What if we had one or more electrons before the collection of our electron at the upper?
Yeah, it doesn't matter. Imagine, okay, imagine that you had already an electron there, okay? And we had these things here. Now let's radiate and radiate the vacuum. Then this will go up there, and we will have 2 electrons, but the same things that we did before, it goes up. The total charge before was not Q. The total charge before, because you had already an electron, is E, and so you understand. Okay, now our problem, yes?
Then in that case, how can, then we don't have difference, between the upper one and the lower one. Then how can we speak about holes and...
Well, it is the same in the sense that if you give more energy, imagine you give this plus an extra energy.
Let's say the energy gap between the layers in the Dirac is comparable to 2m0c².
Right. Let's suppose we give more. Then we excite a state that is here, and as this is continuous, it will go in the corresponding state there. Okay? Now, it will be more difficult in that case to say that the hole left there has a mass equal m0. But you know, as we have already done with the lowest one, and all these particles are identical, they are all electrons, so I imagine that they leave holes that are also all identical. Okay? There are a lot of hypotheses ad hoc for these things. In fact, this is a model that is being cooked up by Dirac, but it's not the second quantization. But somehow, with all these things ad hoc, somehow it works. Right. Before you inject energy there, okay, so in this condition, with no electron in the excited state and all the electron here, I have normalized so that the total charge is 0. That means you say, no, you sum up all of them and you get minus infinity, and the energy you get minus infinity. But you know, what you really measure in nature are only differences. So it doesn't matter if something is minus infinity, you can call it 25, because you measure only differences. So we decided to put it 0. Okay, this is what Dirac did. So we normalize to 0, because what we measure are only energy difference. Okay, is this answer your question? Does this answer your question? Okay.
Can we excite the hole and...
What did you say?
For instance, we excite the electron and then we create a hole, right?
Right, you can, then the hole can get excited. Yes, because you know, what happens is if you give more than this energy, then the hole does not only have its mass energy, but it has also kinetic energy. Okay, but you cannot create, you cannot excite this hole to go there. What can happen is the following. Imagine that here you have a hole, and here you have the electron that from here has gone there. Now, and you have given that amount of energy. Now take away that amount of energy. Take away that amount of energy. Then the things have to go back. And then it means this object, if you take that amount of energy away, goes back into the previous position. And there is no hole, but there is just the normal vacuum. And then the energy is released. So that is what happened. So we had before we had the gamma, and it created the electron and a hole. Okay? So we gave the energy and the thing. Otherwise, we had the hole, and we had the electron. Now we take away from the electron the things, and what happens is the energy is emitted, and these two annihilate. That is why they say matter and antimatter annihilate into pure energy. Because, you know, if you have this electron, and now you take away that amount of energy, he will jump down in his old position, okay? And there will be nothing, like there was nothing before, because this is the vacuum. And so you see, is this a process? Is this process that the electron, you are taking away this energy, annihilates with the positron. Annihilates in the sense that it goes and fills the hole. Okay? Now, let's go. Unfortunately, we have a lot of technical things to do, so let's go to the now the question we want is there a transformation that brings from psi to psi c? Okay, is there a unitary transformation that brings me from particle to antiparticle? Okay, yes, the transformation is there, and now we will find the form of it. It's called charge conjugation, like it was called charge conjugation at the time of the Klein-Gordon. Go and review the Klein-Gordon. Okay, so the operation that makes is called charge conjugation. Now, by the way, this whole theory of Dirac in the book of Greiner is on page don't read everything, okay. Is on page 291. But don't read everything, read only the few things that I'm telling you. Sorry. So now our goal is to build this operator, and this operator is called charge conjugation. It's the operator that takes me an electron and brings me into a positron, charge conjugation. Now, let's see the equation satisfied by the electron. So, the equation satisfied by the electron was IH slash, and let's put an electromagnetic field, because, you know, these two objects have a different charge, so they will feel the electromagnetic field in a different manner. Minus M0C, let's suppose, is a mass, things, psi equals 0. And this is the electron equation. Now, the positron, we said the positron is the hole. It must behave as a positive charge thing. So there is a plus here over C, A slash minus M0C psi 0. Let's call this solution psi C. C stays for charge conjugated particle, and is a positron. Okay, and I want to go from a positive energy, negatively charged particle to a positive energy, negatively charged positron. Positively charged positron. Now, one thing to go from one to the other. How you go from one to the other? Well, for example, change sign here, and we know that A star is equal A, but IH ddx, if you take the star, goes into minus IH ddxi. So the first things we will do is let's take the complex conjugation of this equation. So let's take electron, okay? So the first step we do is complex conjugation. Complex conjugation. Then we get the following equation, IH ddx mu plus EC A mu gamma mu star plus M0 C, all these applied on psi star. Remember, so the goal, now we will do a lot of steps, you will get lost, but let's remember, the goal is to do some changes on this, see which changes on this bring to an equation satisfied by psi C. And then we will gather all those operations and call it charge conjugation. So I put here the charge conjugation is this U Now, the first things I have done is taking the complex conjugate. So this becomes a minus, this becomes with a minus, this is a minus. So if this become the slash is the gamma, so it becomes gamma star, but then I can pull out all the minus and I get this with all plus, okay? So I do the complex conjugate and I get this with a minus equals 0, but then I can take away the minus. Now, but this does not look like this, because there is a minus, and second, there is the gamma and not the gamma star. So we have to find an operator U that brings the gamma star mu into the gamma mu. And actually, not only it brings into the gamma mu, it has to bring into minus the gamma mu. Because if I get a minus, then I can bring it here and get this equation, okay? So I have to find an operator that satisfies this equation. Now, let's write this operator in the following manner as an unknown operator that I will determine times gamma 0. So I can always write everything modulo gamma 0 because, you know, it means this C is U times gamma 0 to the minus 1, and gamma 0 to the minus 1 exists. So I can always write U in this manner as some operator that I have to find times gamma 0. So this is a definition of U. Now, if you take that equation and multiply by U on the left, so let's write the U in this manner, and now let's multiply our equation on the left. We get the following things. So I multiply on the left. If I multiply on the left, I can always, it goes on the left, is a matrix. It does not fill this as matrix because it's a matrix U, 4 by 4, this U, and it goes hitting these, okay? And then on the other, it hits these objects. So the equation that you get is the following thing. So if you multiply by U, the equation you get is the following. IH ddx mu plus EC A mu U gamma star plus M0C M0C U psi star, and here I have psi star equals 0. I have multiplied by a U. But now what I can do is the following. I can insert here U to the minus 1 U, and then if I do this equation becomes the following things. IH d dx mu plus e c a mu u gamma star u to the minus 1 plus m0 c all on u psi star equals 0. Okay? So I have multiplied by u goes through, it goes here, and I have u gamma star, and then I have the psi star. Then the u goes, this is a number, it goes through, it goes there. Well, I can write these things inserting a u to the minus 1 in this manner, because you see these u and u to the minus star to the minus 1 cancel, and I get psi star and gamma star, as I had before. And here I have just m0 times u. Now look, let's now use this u operator that I have not found, but that I know it brings me the minus gamma. If it brings me the minus gamma, so let's use that u that I wrote in this manner, saying, well, it brings me to the gamma mu. Then, you know, this minus 1 I can put there, and I would get this equation. This 1 is minus gamma mu, but I say, let's put plus gamma mu and a minus here. U psi star equals 0. This is exactly the equation of the antiparticle, you see? So it means u psi star is equal to psi of c. So the operator that I need is an operator that I call u, but let's call in another manner, let's call, well, yeah, let's call like we, but it does two things. First, it does the complex conjugate, okay? So it's not actually that one. This let's call u tilde. Then the u tilde is for sure u times the complex conjugation. The operator that makes something complex conjugate is usually indicated with k. So the u tilde I am looking is u times k. But of course now I have to solve this equation because I have to find the u. I mean, all my reasoning was, if a u existed that does this, then from this equation, taking the complex conjugate, I would get an equation that is exactly like the positron equation. And this one would be identified with psi c. So I wanted to do a set of transformation that brings me from this equation to this equation. Okay, change this sign only. I had to do several things. First, take the complex conjugate. Second, suppose it exists an operator that transforms the complex conjugate gamma in minus gamma. Okay, I decided to write in that manner. If I do, then I get really an equation. So if I found an operator that transforms the gamma star into minus gamma, and I do the complex conjugate, I get an equation that is really like the positron equation. Okay? So the u I am looking for, the u tilde I am looking for is something like this u that satisfies this property and multiplied by the complex conjugated operation. Now, let's okay. Let's see, as I wrote the u in this manner, if I can have C acting and telling me things. So basically now we have seen there that psi, let me write here. I don't know where to cancel. Well, let's start here and then I'll cancel. Psi c is u psi star, and this is c gamma 0 psi star. C is an operator, it's not the velocity of light. Huh? This object can also be written as C, and this is psi bar transposed. This is psi bar transposed because, well, why is that is I bar transposed? Let's cancel here. If you do psi bar transpose, this it means psi dagger gamma 0 transpose. This is gamma 0 transpose psi star transpose. Okay. But this object is equal to gamma 0, and this object is thus changing row with a column, so is this. So you see that this object that I had here, gamma 0 psi star, gamma 0 psi star, I could write as this object there, okay? Okay. Sorry. Take it back. This is dagger, and I do the transpose, but the dagger is star times transpose times transpose. So I get gamma 0 psi star, because transport and transport is give the same. Okay. Now let's remember we are looking for this U. This is the central object we are looking, and let's so let's remember this already. Now we have to look for this object, so basically let's write this using this parameterization. We get C gamma 0 gamma mu star C gamma 0 to the minus 1, it has to be equal minus gamma mu. This is the same relation but written in this term. Well, let's remember that gamma 0 to the minus 1 is gamma 0. Okay, and this is very easy if you remember the form of the gamma 0. Do the inverse. Afterwards, maybe in the last two lectures, we will work out some of these detail. But let's see what I get from here. I get C gamma 0 gamma mu star C gamma 0 to the minus 1. This is equal C gamma 0 gamma mu star gamma 0 C to the minus 1. And this has to be equal to minus gamma mu. Okay. Then, okay, let me see if I'm doing correctly. Right. If I bring this on the other side, I get, let me see. Oh, yes. The other thing is there is another identity that is gamma star, gamma mu star, gamma 0 is equal gamma mu t. We'll also verify that later on. So this object there is nothing else than gamma mu t, C to the minus 1 minus gamma mu. T means transposed. So this we have to verify is easy. This is less easy, but we can verify also this. That when you sandwich gamma mu star between the gamma 0, you get the transposed. We will verify that. And then basically the C has to satisfy this relation. This is the C that has to satisfy those relations. Now, so we should build the gamma t, the transport of the gamma, and see which C satisfy that. So now let's cancel this. Let's cancel this. So now remember, U is C gamma 0 K. This was my U tilde of charge conjugation. Now, this is something we have to verify. This is something we have to verify, but we will verify it at the end. Let's see here. We have to find this. Well, the gamma mu t, let's do the various gamma. Gamma 1, if you do the transport, also this will have to be, is minus gamma 1. Gamma 2, if you do the transport, is gamma 2. Gamma 3, if you do the transport, is minus gamma 3 in the Dirac representation. And gamma 0 t is equal gamma 0. Okay, so from here, looking the gamma t, for example, gamma 1 is minus gamma 1. So basically it means it has to commute. The C has to commute with gamma 1. Let's put the gamma 2. Gamma 2, there is a minus, so C has to anti-commute with gamma 2. So basically C has to commute with gamma 1 and gamma 3, anti-commute with gamma 2 and gamma 3. Then the solution of these, believe me, the solution of this is E gamma 2 gamma 0. Okay, so which is the matrix that satisfies this relation is that. So we have finished. This object now is I gamma 2 gamma 0 gamma 0 k. So the charge conjugation, this is 1, is the following. The operator of charge conjugation for the Dirac particle is I gamma 2 times the charge conjugation. Now we have a lot of things to verify, but we will let me do that at the end, okay? Or as an exercise, we have to verify these. We have to verify these and so on. We will do as an exercise. Let me go on with the last symmetry, last discrete symmetry, is the time inversion. Okay, so the charge conjugation for the Dirac particle we have found is done by this operator that is this. Gamma 1 and gamma 3, and anti-commute with gamma 2 and gamma 4. Gamma 0. Okay. Now, the last symmetry we will do as an exercise if time is left or next time to verify all this kind of thing, because this is nice gymnastics with the gamma matrices, so it's very important to do this exercise. Now let's go to another discrete symmetry. So charge conjugation we have done. Let's go to time reversal. So these are discrete operations. So, well, P, the space reversal, that was x, that goes into minus x, t, that goes into t. This one, if you remember, it was I phi gamma 0. Okay? The charge conjugation operation, let's call UC for charge conjugation, that brings the solution of psi into the solution of psi. Gamma is I gamma 2 k, where k is the complex conjugation operation. So this is space inversion, this is charge conjugation. Go and compare with the Klein-Gordon one, because one of the questions in the final could be compare, tell me, write down which is the space inversion operation in the Dirac and in the Klein-Gordon, in the Dirac and in the Klein-Gordon. So do this kind of things. The last things that we do is time inversion. You see, in all these cases, we knew what they were doing on space-time. So time inversion leave the x the same, but it changed the sign of t. And what we looked, this is the space, how it acts on space-time, and this is how it acts on the wave function. So we always answer two questions: how an operator acts on space-time, and how it acts on the wave function. Or another manner that you find in many books is how do you implement that transformation on the Hilbert space. And the same here, the charge conjugation does nothing on space-time. It exchanges psi with psi c. So there is no space-time version of the charge conjugation, but it acts, this is on wave function. Now let's do time inversion, and are the three discrete symmetry. Actually, this is called P, this is called C. It's not the C that appeared there. C is for charge conjugation, so they don't use U tilde, but they use C. And they call this T for time inversion. Now we have to complete this and see O, that is the question, O, it acts on wave function. On the wave function of the Dirac equation. Okay, well, this last transformation is also a Lorentz transformation because this time inversion leaves invariant the 4 distance. The 4 distance is left invariant by that transformation. So time inversion is part of the Lorentz transformation. So it's a Lorentz transformation, but it is a discrete one, and it is an improper one because the determinant of the A, the A mu nu matrix, remember, this was a Lorentz transformation, and this one, a determinant 1, actually plus minus 1. It is an improper one because the determinant is minus 1, and you see from here, the determinant, this A mu nu for the space inversion is minus 1 plus 1 plus 1 plus 1, right? And this has determinant minus 1, so it's in an improper Lorentz transformation, but all the feature of the Lorentz transformation must be there. So now we are looking for that operator T, and see an operator T that when it acts on the old wave function, it transforms into a new one that I call psi prime in the new time. Okay, so this, we are looking for this operator for the, many people say, for the implementation of time inversion on the wave function space or on the Hilbert space. So it is something that takes the wave function, bring into a new one in the new position. Okay? So T is defined in this manner. Is that operator that when you apply to psi, give you a psi prime. Okay. Now, let's start again with the Schrodinger equation. We have, with the Dirac equation, let's write in this manner. And let's do the more complete one, where there is an interaction with the electromagnetic field, with a scalar potential A0 and a vector potential. So let's do the most complete things. And let's call this like our Hamiltonian in X and T. Then it has a form that looks like the Schrodinger equation. Okay. Okay, if let's now multiply by T on the left, T, so I multiply by this operator T on the left, okay? So, this is a definition. This is a definition of T. It's a definition. You have to understand nothing. A definition is like a postulate. I tell you, that is made of wood. I mean, and you cannot see, so it's a definition. So I define an operator T that does this action. It might not exist. We will end up saying it does not exist, and then you are right. But first, let's postulate what we are looking for. So we are looking for an operator that does the following. It acts on psi and produces a new psi. Psi prime means a new psi. It rearranges the various components of psi, and it changes T into minus T. So this is a definition of T. I put 3 things.
At the same position?
No, in the new thing. Oh yes, of course, because you know that the time inversion does nothing on x.
So we get
The same position.
but the time will change.
Yes, the time will change because we are implementing this. So the time is changed. This t prime is minus t. I'm doing the time inversion. Okay? So if you don't like t prime, let's call it minus t. I am implementing the time inversion, so I know that on space-time, xt goes in x and minus t. Look there, time inversion. And I want to know how the wave function will change, so I call it psi prime.
No, my problem is how is it possible the same position?
Because time inversion does not change the position. Look there. The time inversion does not change the position. I am implementing time inversion. Time inversion leaves you there, but it changes your time. As simple as that.
Maybe the question is like space and time are not separate. Maybe, I don't know. Okay,
So tell me what you don't understand. Because, you know, do you agree that time inversion is this? Time inversion, it means you invert only time. And all the rest you leave the same. You see, can I do? Yes. If I invert only time, this square remains the same. This does nothing. The distance remains the same. Okay, so it's an operation that is allowed. It's a Lorentz transformation, a very particular one, but it's a Lorentz transformation.
Okay, maybe the result will clarify.
Huh?
Maybe the result. Let's.
Oh, the result will be very complicated and you will be more confused than you are now. So I am implementing this at the space-time level. I know what it is. I want to know what it is at the wave function level. So this t, you see this t, and now I'm looking for the t. So let's take this equation. Let's multiply by the left by t, and then this is equivalent to the following things. Is equivalent to minus t ih t to the minus 1, derivative with respect to t prime. Let me finish and then x t prime. No, sorry. Let's do this. I take this, I multiply by the left by t. Okay? But you see, this t minus 1 and this t cancel, so it's like having multiplied to the left by t. Here, this t and t prime is the same as having multiplied by 1, and the net result is having multiplied everything by t. So even these complicated things is the same as this one having multiplied by the left by t. Now, this object and this object, we know what they are. They are psi prime x t prime, psi prime t prime x t prime equal t h t to the minus 1. Now, as this is this object, let's this one, let's say is t prime, that is minus t. Why I do that? Because I bring a minus here, and that compensates this, and I have t ih bar t to the minus 1. So this equation, first I prove that this equation is the same as this. Why? Because I have t on the left, t and t prime that cancelled, t on the left, t and t prime cancelled. Yes? Yes, because it acts only on wave function. I mean, here, you mean? Yes, this one, because it acts only on wave function. Remember, this is an operator that acts only on wave function. I am looking for the operator to see what it does on wave function. Okay? So, then I call this t prime, that is minus t, but I bring the minus out here, okay? And let me call these objects, so, okay. If we want, so this is the final equation, but we know that if we want the Dirac equation to be covariant, we must have the following equation, t prime psi prime x t equal h x t prime psi prime. Okay? So this is if we want the equation to be covariant, to maintain the same form, sorry, plus. If we want that this equation is covariant, like all the equations should be under a Lorentz transformation, if that means maintain the same form. So to maintain the same form. Then this happens if this object is equal to this. It means that t, first things that it does, it makes the complex conjugate, because if it makes the complex conjugate, there is a minus, and they get a plus. Okay? And here, what has it done? Well, on the Hamiltonian, the only things it can do is change time. Okay? So now you see that this form, so provided that t to the minus 1 is equal to minus I, provided that this equation that I have obtained has the same form as that one, so is covariant. So the first things that it has to do is the following things. Second, I want that it maintain the same form. But let's look here what happened. I have t to the minus 1. So let's go and see the detail. Well, under time inversion, remember that there were various things. Into t, there was a, and there was these things. There was alpha, and so on. So I want that this object goes into this one. And how does for example, the electromagnetic potential change? Well, the electromagnetic potential is generated by currents, right? But t, change in time, change the direction of the current. So this one will go into this. And the scalar potential like the Coulomb one is generated by static charges. So no current will change sign, and the electromagnetic potential will go into the same things. Okay? Then all this one, well, this one will not change because x, the derivative, the gradient will not change because x does not change under the rest of the things. Now, let's look here. I have this thing that does not change, this thing that change, okay? So let's now go and look at these objects. So let's remember this, and let's look at this object, t to the minus 1. That is this object. Knowing this, we get minus t c alpha t to the minus 1 minus IH square minus ECA plus M0 C T B T to the minus 1 plus EA0. A0 is not changed by this, so I leave it as it is. This one I have changed, let's see, T, no, let me do in detail, Becomes a long thing, but I have to do in detail. So, T, H, T to the minus 1. H is that expression over there. So I have T, C alpha, T to the minus 1. Then I multiply by T minus AH, T to the minus 1, then I have t gradient t to the minus 1 minus EC t a t to the minus 1 plus m0 c squared t beta t minus 1 plus c t a0 t to the minus 1. I have sandwich between t and, you see, these two cancel, and the first term is sandwiched between t and t minus 1. The second term is sandwiched between t and t minus 1, and so on. By the way, let me, I have to put some square here. I have a square, and then I have a squared, here. Now, let's start seeing what I get. I get a minus from here, because it makes the charge conjugate, and I get a minus from here. So I get minus t, so I have two minus. This because we know it does a complex conjugation from here. Here on this it does nothing, and then it changes sign on this, so I have a minus from there, a minus from there. I can bring out, I have t c alpha t to the minus 1 minus IH gradient minus E over CA plus m0 c t beta t to the minus 1 plus EA0. Okay, so I have a minus here, and I have left all the rest. Coming from these things, this is left invariant, this one goes into I plus, and this one goes into minus A, and so I collect this A, this minus, and this minus, and I bring it out, and I get these things. Now you see, I want that this TH t to the minus 1 is equal h x t prime. I want that it maintain the same form, otherwise it's not covariant. Then the only solution of this happen only if you pay attention, look at the form that the Hamiltonian has, and look at this. This can happen only if t alpha t to the minus 1 is equal to minus alpha, and t beta t to the minus 1 is equal beta. Okay, if this change sign, then I get a plus, okay, and I get exactly the same things as there. If this I get a plus, I get the plus beta like there. So these are the two conditions that I have to get in order to pass from this equation to an equation in the new variable, in the new time, but where the Hamiltonian, the only thing that has changed in the Hamiltonian is t, because I want form invariance. Form invariance, so that means this must have the same form as the previous one. Okay, covariance means form invariance, not equality, form invariance. The equation has the same form as the previous one, but in the new variable. So the wave function change, t change, but these I want that it does the same things as before, but in the new variable. So these are the t. The t has to satisfy these two properties. So let me now cancel. And let's write down that t has to do the following: alpha t to the minus 1 minus alpha, and t beta t to the minus 1 equal beta. But t, the first things that t did, it was changing IH into minus IH. So it has a complex conjugate, and let's call the rest T0. So the t is actually complex conjugation times T0. So this relation becomes, remember, T0 times K. K makes the complex conjugate. So you get T0 alpha star T0 to the minus 1 must be equal to alpha. and T0 beta, beta is real, is 1 minus 1. So when you do the complex conjugate does not act, T0 to the minus 1 equal beta. So the T I have written in this manner because I know that the first things it does is complex conjugation. Okay, well, you can turn these things into relation among the gamma. This means T0 gamma I star T0 equal minus gamma E, and T0 gamma 0 T0 minus 1 is equal gamma 0. Well, let's remember the form when alpha, and you build the alpha star, basically the only matrix that is imaginary is alpha 2, because it's built from the sigma 2, and the sigma 2 are the only one that is imaginary. So these things, now I can cancel here. I can cancel here, and this one, for example, this one becomes the following. T0, alpha 1 is real, so alpha 1 star is equal to alpha 1. T0 to the minus 1 equal minus alpha 1. Then I have alpha 2. Alpha 2 is the only one that is imaginary. So as it is imaginary, it changes sign. I have a minus sign, so I get a plus sign. T0 alpha 3 is real, so I get minus alpha 3, and then I have beta equal beta. Okay, so these are the 4 relations that T has to satisfy. Then I can show to you, at least we can verify, we will verify next time, that T0 is alpha 3 times alpha 1. If you want to use the gamma matrices instead of the alpha, then is minus I gamma 1 gamma 3. So this is T0. So let's get back here. T is T0, and we know E gamma 1 gamma 3 times the complex conjugation, or plus I gamma 3 gamma 1 K. Okay, so we have found, well, of course we have to check a lot of things. We have to check, so one exercise we have to do is to see if this satisfies this relation, because I only said the solution is this. It's not, I don't have a manner to derive it, but I can at least check, put it back and see if it does. And this is an exercise we will do. But now we have completed our scheme here, because now we know that T is equal E why there is an I that is wrong. No, is plus, so is plus. If I want to write it in terms is plus. So the T, the time inversion relation is I gamma 1 gamma 3 complex conjugate. So now I have all 3 discrete relations. And you can say, well, yes, discrete relation, but P and T, I understand. C has nothing to do with Lorentz invariance. It's true, has nothing to do with Lorentz invariance. But, you know, the antiparticle appeared because we wanted the Lorentz covariant equation like the Dirac one, and we insisted in having an interpretation of that. It was first ordered, so we got a probability interpretation, but then there was the business of this Dirac C. The solution was the whole theory, and the whole theory, as I explained today, immediately produce the concept of antiparticle. Then there is a charge, and an antiparticle has the same mass as a particle but opposite charge. So as antiparticles are present because of this whole theory, there is a symmetry that exchanges them. Well, a miracle that you will see next year when you do, there are many symmetry that violate some of these. For example, the weak interaction violate time inversion. You will see. And why? The neutrino are left-handed. You don't have neutrino that are right-handed. So if they are left-handed, and you cannot find any neutrino that are right-handed, you can only find antineutrino, then there are a problem. And in fact, the weak interaction, that the interaction responsible for the beta decay, that you take a neutron and after, on the average, every 15 minutes, a neutron transform into a proton, an electron, and an antineutrino. And this is responsible for this is the weak interaction, does not violate, it violates the parity or the time inversion. It's not a symmetry, space inversion is not a symmetry of the weak interaction. And so on, others are violated. But any interaction, the gravitational one, the electromagnetic, the weak, and the strong interaction, they preserve the product of the three. These three means not each single one, but the product of the three is always preserved. So this is called Pcp Theorem. Any interaction satisfies the product of the three. That means if it is invariant, for example, a theory could be not invariant under P. Fine, like the weak interaction, but then it is not invariant under C and under T, and then all together. So, for example, not invariant, and invariant, and all together is invariant, right? You understand? So, or otherwise it can be invariant, invariant, and invariant. Or it can be non-invariant, non-invariant, and invariant, or this and that. Then all together is invariant. So the product of the three, P, C, T, is always an invariance, and it was proven in the 50 by Zumino and by Luders and few others. This is an important theorem that you will see in field theory. In the book is roughly mentioned. Now, the time inversion things, the only things I took very few things from the book, and they are, the time inversion is on page 312, and are just the first few pages, okay?